So I'm going to talk about cost sharing methods for scheduling games under uncertainty, and this is joint work with Giorgos, Christodoulou, and Alkmini, Sgouritsa. So let me pictorially try to introduce the model so you get a sense of what the contribution is here. So we have a set of machines. In this example, we have just two machines, which are defined by the cost function, how their cost changes as the users, which you see down here, start using those machines. So you have these plots up here that you see as the number of users using the machine increases, so does the cost of that machine. So there's one cost function here, one different cost function there, and that essentially characterizes what the inefficiency, what the cost induced by the users are. And the setting we have in mind is we have this system set up, and each day some subset of these users arrive and decide to use some of these machines. So in this example, there's 3 users going into the left machine, 3 users going to the right machine. So then we can compute the prices, the costs, by looking at exactly when 3 players are there, what's the cost, and same thing on the other side. Make sense? So the next day, different subset of users arrives. Maybe it's just one of them, causes a specific cost, and so on. Third day, totally different subset. And totally different costs. So if you look at this one, so our goal throughout this talk will be to try to minimize this total cost, try to be efficient, try to schedule people so that the total cost is minimized. And if you look at this one, maybe you've already noticed that it's not very efficient, right? So you look on the right hand at least, if you see that, well, we've reached that point after which there's no additional cost by adding one more user on the right machine. So we could just move all these users to the right machine without suffering any extra cost. So this schedule, for example, is inefficient. But throughout the talk, of course, this is why these are called scheduling games, the participants are not really going to care about the social costs. Rather, they just try to minimize their own cost. And again, this is the point where you observe that I haven't really defined a game yet. I've told you what the strategy set is. Each player chooses one of the machines. So the strategy set is a set of machines for every player. But I haven't defined the utility yet. So in order to define the utility, I need to tell you how this cost that they generate is shared among them. This is where the cost sharing, our handle into this problem lies in this cost sharing mechanism. So we decide how to share this cost among them. So one very simple approach would be to just say, let's share it equally, right? So equal sharing is one way of going about this. And then in this case, all the users on the left here would be suffering a cost of around 300 each, if you see that the total cost is 900. And the users on the right would be suffering a cost of around 250 each, because there's 4 of them, and the total cost is 1,000. And if you think of it as a game, now that we have a utility function, once we've set up this cost-sharing method, we have a utility function for every possible strategy profile. Now we can think about incentives. What would this be a stable schedule? And you will quickly see that one of the left users would be happy, let's say this one over here, would rather actually switch to the right machine because he's currently paying around 300. If he switches, there are going to be 5 people here paying a total cost of 1,000, so 200 each. That's much better. And in fact, if you keep iterating, you'll see that all of them will want to switch, and you'll get an equilibrium where everybody uses the right machine. So throughout this talk, our goal will be to design such cost-sharing mechanisms like this one with the goal of optimizing the quality of the equilibria. Okay? And the question is, what is the design space? Okay, so the cost-sharing mechanisms is what we're designing. How general, what power do we have in design? What information do we have in designing them? So specifically in this example, this is what we will call an oblivious cost-sharing mechanism. That is, the equal sharing mechanism doesn't really look at what happens in the rest of the system, right? So it just looks at the jobs that arrived and says, whatever jobs arrived in my machine, so this machine just looks at the jobs that arrived and just splits the cost equally among them. So this is, in general, all oblivious cost-sharing mechanisms will have that property that they ignore what's happening. Both the machines that are not part of, so each machine essentially ignores every other machine and what other users are present at that particular day in the system. So it looks something like this, right? So the cost-sharing mechanism here would essentially, an oblivious one, like equal sharing, but it can be more general than that, essentially ignores the rest of the system, as well as which of the users are actually present in the system that particular day. The good thing about this is it's very scalable, very decentralized. When you add one more machine into the system, you don't need to care about the rest of the system. You just set it up. It doesn't affect anything else. The bad thing, of course, is you have limited power in designing your cost-sharing mechanism, so you might be unable to get better equilibria. On the other extreme, there's omnipotent cost-sharing, where you have full information. You know exactly what all the other machines are like in the system, what their cost functions are like, what other people are actually present that day, so you can design your cost-sharing mechanism using that information to design exactly the equilibria that you want to optimize for the cost. Right? So this is very strong. So you can see these are two very extreme options. Oblivious knows nothing. It's very local and myopic. Whereas omnipotent knows everything, and you can imagine the difficulty here would be that maintaining this kind of a cost-sharing mechanism means you have all this centralized information. You keep track of everyone who's joining the system at any given day. And by the way, another difficulty would be that it might be very sensitive. Like one person joins, and then the whole thing changes, so it's hard for people to predict what their costs will be. So the main focus of this talk and our paper is on what we define as the resource-aware cost-sharing mechanisms. And this lies between these two extremes, between oblivious and omnipotent. And what we're going to be doing is we're assuming still that we cannot keep track of which users are present one day or another. So we don't know what users are active in the system at any given time. But at least we know what the system is like. We know what other machines exist in the system and what their cost functions are like. So this way, that allows us to essentially optimize for to use this information, this extra information, to possibly get better price of anarchy, better equilibria. And this is very reasonable in the sense that you can imagine in many systems, the machines don't change that radically from day to day. You have more or less a fixed set of machines. The users change, and those we're not going to be depending on, but the machines are going to be more or less stable. And the question, of course, is can you use this extra information, the fact that in this case you don't know exactly these arrows, you don't know who else is present, so this machine only knows what users are using itself, and it knows what other systems, what other machines are in the system, but it doesn't know what other users in the system. Is that clear? So this is an important part to understand the model before we move on. So that's what we're focusing on. We think it's a very reasonable intermediate model. And the question is, what can we do compared to the previous work? So bear with me now with some more formal definitions of what we have. So we have a set M of M machines. So what is a scheduling game? We have a set M of M machines and a set N of N agents. And agent I needs one machine to process a job with weight Wi. So they can have different weights in some of our results. But for the sake of this talk, just assume that all the weights are 1. Although I will be using the notation Wi for generality. And this cost, so in each machine, as I mentioned, has a cost function Cj. So each machine J has a cost function Cj of L, where L is the total load, the sum of the weights, or the number, if you assume the weights are 1, the number of users using that machine. And the cost function we're going to assume is 0 when nobody's using the machine. So there's no cost if nobody's using it. And as I mentioned, the strategy set of every player is a set of machines. And this leads to a strategy profile S. Capital S sub J of S is the set of jobs using machine J in profile S. And L sub J of S is the sum, essentially the load on a particular machine J in the strategy profile S. Okay? So what is a cost-sharing method? Essentially, the cost-sharing method for a specific profile S defines psi ij, which is the share of that cost that player I is responsible for. And we say that it is budget balanced, and this is going to be an important point in this case. So it's budget balanced, it's natural, you can predict what this is. The sum of the cost shares adds exactly to the cost that they created. So they're exactly dividing up between them the cost that they created. So this has been a standard assumption in previous work. This is one of the deviating points in our work. We're actually going to be relaxing this, maybe overcharging. And the other thing which we're not going to be relaxing is pure Nash equilibrium existence. So we want cost-sharing functions that guarantee that there always exists this pure Nash equilibrium, when we call these stable. One more slide with theoretical definitions. So we measure the efficiency of a schedule S using the cost, the sum of the costs across all the machines. And this is what we're trying to minimize. These are all kind of natural definitions here. And given a class of games G, so we're going to be looking at big class of many games, we let F of G be the set of all possible schedules, and E of G be the subset of these schedules that are pure Nash equilibria. So now, most of you probably already know, but for completeness, the price of anarchy of a class of games G is the supremum over all the games in G of the worst social cost over equilibria in this game compared to the social optimum. Okay, so the worst equilibrium compared to the optimal solution across all games in this class. And the important thing to emphasize is that we may overcharge. We might take the cost of a machine and raise it artificially, add more cost for incentive reasons, which means that the sum of the cost shares will actually add up to some C hat of S, which can be greater than the actual cost. But, very importantly, otherwise we would be cheating, we're measuring the price of anarchy. We're measuring our cost in equilibrium with respect to the additional artificial cost that we added, but comparing it to the benchmark still is the same. So we still compare it to the optimal solution if no cost had been added. Okay, so that's very important. So we add costs for incentive reasons, but still measuring, we're suffering for those improved incentives. And also, I'm going to be mentioning at some point the price of stability. It's just the best equilibrium rather than the worst. So it's minimum instead of maximum here. OK, so in terms of related work, there's a long literature on cost sharing and coordination mechanisms that are closely related to this. But the most closely, I don't have time to review all this, the most closely related results are the one by Chen, Ropgarten, and Valiant from 2010, where they studied network design games. So this is a special case where these cost functions I described before are constant. Think of a network. You're either creating a bridge. You either create it or not. Once you've created it, there's a constant cost that you suffered. Everybody who's using it, there's no additional cost. And the agents in that one, it's more general in the sense that you can use multiple machines. Right? So you can have multiple resources in each. So the strategy space is richer. And they have a very interesting characterization of all the stable cost-sharing protocols. What does it mean? It's strange to figure out what is a stable protocol, what guarantees equilibrium existence. And then there's another paper by von Fankelhausen and Harks that studied more general cost function. This is even more closely related to ours, and I'll be citing this throughout the results. That also considered extensions to matrix. It's not just for scheduling games. The important deviation of our work compared to the previous work is that both of these papers are restricted to budget balanced, whereas we are going to be overcharging and trying to understand what the power of overcharging can be, and that they're only looking at the two extreme protocols that I mentioned at the beginning, either omnipotent or oblivious, whereas we're trying to understand the power of this middle ground model here, the resource-aware model. OK, so let's start with the easiest case, which is convex functions. And we're going to be using a global ordering of the players. This is an important tool that we're going to be using throughout. We assume the universe of the users are ordered in advance. So here, there's, in previous work from Moulin, there's this incremental cost-sharing protocol that does the following. Order the agents based on pi, and then charge each agent the cost equal to its marginal contribution, as if they were arriving in that order. And this is the formal definition. The way to think about it, if you have this cost function, the first player, you have a set of players, you treat them as if they're arriving in the order of pi. First one pays this cost. The second one pays the difference between these two costs. The third one pays the difference between the marginal contribution, how much they're contributing in that specific order. And the very nice thing about this is that it's stable, it's budget balanced, and oblivious. You see, it doesn't use any information. So it's really, really simple. It actually achieved a price of anarchy of 1 for unweighted agents and convex functions. One of the open questions, I should mention it now in our result, is whether we can get a good upper bound here for resource-aware. This is one of the open problems. We don't know for convex functions and weighted players whether resource-aware can actually help us here. But this doesn't work for weighted, this specific cost-sharing method. OK, so now that we looked at the easy case, let's go to the other extreme and look at the very hard case, general cost functions. What can we do there? So our first result is that every stable, budget balanced, And resource-aware mechanism has a price of anarchy of omega of m, the number of machines, for general cost function. This means even if we get this extra information that resource-aware protocols have, this is not going to be useful in general. But what if we allow the use of overcharging? Well, in general, again, even if you do not restrict yourselves to budget balance, still you cannot get a constant. We get a lower bound of omega root m, and it's quite non-trivial to get the latter one. So the first one's pretty easy. The second one is trickier because the design space is so much richer. Essentially, you can overcharge in very different ways and use that all this extra information. Just to give you a sense of how our lower bound works, imagine you have m machines with all of them having a cost of 1 for one agent, and going to infinity the moment you have a second agent using them. So essentially, you have a capacity of 1 and a cost of 1. And then you have one more machine that has a capacity of m, and its cost is root m, and it goes to infinity if you get anything more than root m. So the easy thing to observe is to get a weak version of the top result. If you had exactly m people using these machines and it's budget balanced, that would be an equilibrium. They're all paying a cost of 1. Nobody wants to move to the other one. But if you move them to the other one, you would actually get much, much better. The second one is much trickier, actually, because you can overcharge here in very strange ways that depend on somehow trying to enforce something not being an equilibrium. And therefore, it's really hard to kind of convince yourself and prove that that any stable cost-sharing policy will not be able to guarantee a good price of anarchy. But now that we cannot do this very general thing, are there reasonable types of cost functions that we can deal with? And one very reasonable class is the class of concave functions. Essentially, the cost goes up, but then at some point, kind of, the more people that use a machine, the cost doesn't keep increasing. And for those, we know that if we restrict ourselves to budget balanced and oblivious cost-sharing policies, then the price of anarchy is at least n. We show that, so that it's very bad. And the observation is that when you have a concave function, you know that the best thing to do is everybody using exactly the same one machine. And although this lower bound is for unweighted, our upper bound is going to be for weighted. And if I allowed you some time, I don't have the time to allow you to think about it, but it's kind of strange. How do you use this extra information, the fact that you know what other machines are doing, to really try to figure out how to get a good price of anarchy? I don't have to go the time to go through the definition of this cost-sharing method, but the idea is, in some sense, locally, each machine pretends that it's the only one in the system, and that all the load that it sees is the total load in the system. And somehow tries to, given that assumption, either decide whether it should push people away or keep people in there. And the way this information, the use of the other machines being in the system, this extra information comes in, is through these variables that I don't have time to define. I'm happy to chat about this offline. But the nice result is that we get stability, budget balanced, and through this resource-aware mechanism, we actually get a price of anarchy 1. So we use the resource-aware information to actually drop the price of anarchy from n to 1. So we actually enforce the optimal solution as the only equilibrium. The next class that we consider is both convex and concave. And in that case, we already know from Funkelhausen and Harks that no budget-balanced mechanism can guarantee a price of stability even, not price of anarchy, not even price of stability, better than a logarithmic approximation. Even if it's omnipotent, even if it knows everything. So this is a very strong negative result. So therefore, if you don't overcharge, it's hopeless. Even if you knew everything, there's no way you can get better than a logarithm. So again, I don't have enough time to go into the details, but what we're doing is we're overcharging in a way that uses the structure of the optimal solution, because you know what the other machines in the system are. So we overcharge in this way, and that allows us to essentially then use our previous mechanisms, the incremental cost sharing for convex machines and our concave cost sharing for concave machines. And on this overcharged costs, it actually achieves a price of anarchy of 2. So again, these are, if you had the time to think about how to use this extra information. It's non-trivial. We have this extra information because we know what other machines are available in the system, but how to leverage this to get better price of anarchy is not obvious. And here we also need to leverage overcharging as well, which I think is very reasonable. We're not undercharging, but overcharging, if it improves the price of anarchy despite the extra costs, why not? Finally, we have some results for two-machine instances, so instances that have just two machines, but arbitrary types of cost functions. And there, if we let alpha of s be the highest priority agent in the first machine and beta of s be the lowest priority agent in the second machine, then we have this increasing, decreasing mechanism that essentially, for the one machine, it charges everything to alpha of s, and the other machine, it charges everything to beta of s. And for this one, we actually also get a price of anarchy too for arbitrary cost functions. And one interesting thing about this is that it's stable, but it's not a Shapley value variant. So for those of you who know what the Shapley value cost sharing is, this is one natural way to guarantee stability, existence of pureness equilibria. This one is not one of those cost functions, one of those cost sharing mechanisms. And finally, a lower bound, which says that we could not hope for much better. In fact, there's a price of anarchy lower one of 1.36, even for two machines, and even for the special case of convex and concave cost functions, for which I mentioned before, we already get a price of anarchy of 2, upper bound. So this is a lower bound that applies both to this and to the previous slide. So to conclude, what we defined here is this resource-aware cost-sharing model, which I think is a well-motivated middle ground between the omnipotent and the oblivious model. For non-trivial use, using in a non-trivial way the extra information that this provides, we show that that enables improvements. We also show the power of overcharging, that this can lead to improvements despite the additional cost, because you are causing people to suffer extra costs, but that still creates so much better incentives that they're better off. And one result that I didn't mention, by the way, is that for omnipotent protocols, overcharging can allow us to get price of anarchy of 1. Whereas if you had to be budget balanced, again, from von Funkelhausen and Harks, we know that logarithm is the best we could ever hope for. And in terms of open problems, there's several weighted upper bounds that are missing from our results that are interesting, but also I think even more generally, applying the resource-aware model, the idea that you might not know the participants, but you know the machines, you know the system, in other settings is even more interesting and more general. Thank you.